In this video, I'd like to talk about free energy and chemical reactions. But first, let's pop back to one of the sections from earlier in the chapter we skipped, namely chapter 17.4 on free energy. What is free energy? Free energy, sometimes called Gibbs free energy, after Josiah Willard Gibbs, who discovered all of this in the late 1800s, is a thermodynamic function that we made up that is used to predict whether or not a process is spontaneous. So free energy is defined, it's often called the available energy. It is the amount of energy that a system has that is capable of being harnessed to do useful work. So we can calculate the free energy of a system, G, as the enthalpy of the system, H, minus the product of the temperature and the entropy of the system, S. Well, we don't particularly care about the absolute free energy, and we certainly can't measure the absolute enthalpy. We're more concerned with free energy changes in chemical processes. So for a process, delta G, the change in free energy, is equal to delta H, the enthalpy change, minus the product of the temperature and the entropy change. This is the single unified equation that we use in order to determine whether a process is spontaneous or not. In many ways, this is the most important equation in the entire class. Okay, now, a process is spontaneous in the direction in which free energy decreases. Think about it. If I have a spontaneous process, that means that free energy is flowing from the system to the surroundings in order to do useful work. In that particular case, the system is losing free energy, so that means the change in free energy is negative. So for a spontaneous process, delta G is negative because the free energy of the system decreases. That is our primary criterion for spontaneity, a negative change in the free energy of change in a process, delta G. Now, notice, based on the equation, that spontaneity, that is having a negative value of delta G, is favored by exothermicity and an increase in entropy. Because if delta H is negative, that tends to make delta G negative, and therefore the process spontaneous. Correspondingly, if delta S is positive, meaning that entropy is increasing in the process, that also favors spontaneity because subtracting the positive temperature times the positive entropy change delta S tends to make delta G more negative. So how all does this play out in terms of predicting for a given set of delta H and delta S whether a process will be spontaneous or not? Well, let's look at all possibilities. We begin with our most important equation, delta G equals delta H minus T delta S, and let's consider the four possible combinations of signs of delta H, the enthalpy change, and delta S, the entropy change. In the first example, if delta H is negative but delta S is positive, meaning we have an exothermic reaction in which entropy is increasing, delta H is negative, and we're subtracting temperature times a positive delta S, we see that delta G will always be negative. There is no way with a negative delta H and a positive delta S for delta G to be positive. Therefore, such a process is spontaneous at any temperature. Correspondingly, if the situation is reversed, if we have an endothermic reaction in which the entropy is decreasing, delta H is positive, delta S is negative, there is no temperature at which delta G can be negative. Therefore, the process is non-spontaneous at any temperature. It cannot be spontaneous in the forward direction no matter what the temperature. In our third case, we have an endothermic reaction, positive delta H, in which entropy is increasing, positive delta S. That would be a positive delta H, which disfavors spontaneity, but a positive delta S, which favors spontaneity. We see that delta G can be negative, and therefore the process can be spontaneous, only when the magnitude of T delta S is greater than the magnitude of delta H. That occurs at high temperature. So if you have an endothermic reaction but has an increase in entropy, higher temperature favors spontaneity. And then finally, our last possibility is when we have an exothermic reaction that results in a decrease in entropy. The negative value of delta H favors spontaneity, but the negative value of delta S does not. Therefore, we will have a spontaneous process with a negative value of delta G only when the magnitude of delta H is greater than the magnitude of T times delta S. That will occur at low temperature. So, now let's move on to Gibbs free energy changes and chemical reactions. For this, we're going to focus on delta G naught, the standard Gibbs free energy change. That is the free energy change that occurs when the reactants in their standard states are completely converted to the products in their standard states. And for refresher, standard state means pure elements. It means 1 atmosphere pressure, 298 Kelvin, 1 molar solutions. So, for example, if we consider nitrogen and hydrogen reacting to form ammonia, as written, this has a standard Gibbs free energy change delta G naught of negative 33.3 kilojoules per mole of reaction. What that means is that if I were to take 1 mole of nitrogen and 3 moles of hydrogen in their standard states and completely convert them to 2 moles of ammonia, even though I couldn't actually do this, that system would release 33.3 kilojoules of energy. Or we would say that 33.3 kilojoules are available to do useful work. Now, the fact that it's negative tells us that this is a spontaneous process. So, why is this useful if we can't measure it directly but calculate it? Well, because we can use standard conditions, that is delta G under standard conditions, to compare spontaneity of processes in which we are at non-standard conditions, which we'll get to in a couple of units or sections. So, how then do we calculate delta G naught, the standard Gibbs free energy change for a chemical reaction? Well, we have 3 ways to do it. The first is to use the standard enthalpy changes and the standard entropy change from the thermodynamic tables. As we learned in Chapter 6, if we can look up the standard enthalpies of the products and reactants on the thermodynamic tables, we can use this formula to calculate delta H naught, the standard enthalpy change for the reaction. Likewise, we just learned in this unit that we can calculate the standard entropy change of a reaction if we can look up the standard entropies of the products and reactants on the thermodynamic tables. Having calculated each of these, we can then use our master equation, delta G naught equals delta H naught minus T delta S naught, to calculate delta G naught, the Gibbs free energy change, and from that determine whether the process is spontaneous or non-spontaneous. A second method is to use Hess's law if we have reactions for which we know delta G naught, the standard free energy change, and can manipulate the equations to come up with our desired equation. This should look fairly familiar. So for example, if equation 1, A plus 2B reacts to form C, has a free energy change equal to delta G naught sub 1, and if equation 2, C reacts to form 2D, has a standard free energy change of delta G naught 2, well, we see we can obtain a third equation by simply adding these together. C cancels C, and we get A plus 2B reacts to form 2D. Delta G naught for this reaction should simply be equal to the sum of the standard free energy changes for the constituent reactions. Keep in mind, just like we saw earlier, that if we were to reverse an equation, we would change the sign of the standard free energy change, and if we were to multiply the equation by some coefficient, we would multiply delta G naught by that same coefficient. Our third method of calculating delta G naught is to use what are called the standard free energies of formation, or delta G naught sub F. This is the second, well, you'll see in a second. So, delta G naught sub F is the standard free energy of formation of a particular compound. It is defined as the free energy change that accompanies the formation of 1 mole of the compound from its elements in their standard states. Okay? Very reminiscent of the standard enthalpies of formation, which we learned about in Chapter 6. The difference is that these are free energy changes, not enthalpy changes. The values of the standard free energies of formation of various compounds are found in column 2 of the thermodynamic tables. And just as we saw with delta H, we can calculate the standard free energy change of a reaction by taking the sum of the standard free energies of formation of the products multiplied by their stoichiometric coefficients and subtracting the sum of the standard free energies of formation of the reactants multiplied by their stoichiometric coefficients. Okay? The limitation is that because the values of the standard free energies of formation are measured or tabulated or calculated at 298 Kelvin, we can only use this if the temperature of the reaction is 298 Kelvin. Okay? What if we're at some other temperature? Then we simply revert to our master equation, delta G naught equals delta H naught minus T delta S naught. Because delta H naught, the standard enthalpy change, and delta S naught, the standard entropy change, are assumed to be temperature independent, and they are in this class, then we can simply calculate those using the thermodynamic tables, plug in whatever temperature we're at, and then calculate the corresponding value of delta G naught at that temperature. Remember, delta G naught, the standard free energy change for a reaction, is a function of temperature. It varies with temperature. That's very important. So, for the remainder of the video, let's just do a couple of examples of one example of each of these. So, in question 1, the decomposition of ammonium dichromate produces nitrogen gas, water vapor, and chromium 3 oxide. Well, we know we're going to have to write an equation, so let's just go ahead and do that. Solid ammonium dichromate decomposes to form nitrogen gas plus water vapor plus solid chromium 3 oxide, and there's our balanced equation. Use the data in the thermodynamic tables plus the standard enthalpy of formation and the standard entropy of ammonium dichromate to calculate two things. First of all, delta G naught for the decomposition reaction, and then second, the standard free energy of formation of ammonium dichromate. So let's do those in 2 steps. So for question A, calculating delta G naught for this reaction, we're going to use the most generally useful form, delta G naught equals delta H naught minus T delta S naught. Before we can plug in, we need to know delta H naught and delta S naught, so we're going to calculate those. Delta H naught then is going to be the standard enthalpy of formation of nitrogen gas plus 4 times the standard enthalpy of formation of water vapor. Pay attention to physical states. You want water in the gas phase, not the liquid phase. Plus the standard free energy of formation of chromium 3 oxide minus the standard free energy of formation, the standard enthalpy of formation of ammonium dichromate. Looking at the values in the table, these are, obviously this is 0 because it's a pure element, plus 4 times negative 242 kilojoules per mole, plus negative 1,128 kilojoules per mole, minus negative 23 kilojoules per mole, giving me a standard enthalpy change for this process of negative 2,073 kilojoules per mole. It is a highly exothermic process. I can do the same to calculate the standard entropy change for this reaction. Delta S naught is going to be the standard entropy of nitrogen gas plus 4 times the standard entropy of water vapor plus the standard entropy of chromium 3 oxide minus the standard entropy of ammonium dichromate. Plugging in, this gives me plus 192 joules per mole Kelvin. Remember, the standard entropies of pure elements are not 0. Plus 4 times 189 joules per mole Kelvin plus 81 joules per mole Kelvin minus 114 joules per mole Kelvin. And that gives me a standard entropy change for this process of plus 915 joules per mole Kelvin. So let's ask ourselves, is the sign and magnitude of delta S naught for this reaction consistent? Does it make sense? Well, if we look at the equation, we'll see we have 1 mole of solid forming 1 mole of solid plus 5 moles of gas. So yes, we would expect that the positional probability of the particles that make up the system is increasing. The products are definitely more disordered and more random than the reactants, so we would expect a large positive standard entropy change, which we definitely see. And now finally, to calculate the standard free energy change, delta G naught equals delta H naught minus T delta S naught. We'll use the values we just calculated, negative 2,073 kilojoules per mole minus, I may have forgot to mention, but we're calculating this at 298 Kelvin, times plus 915 joules per mole Kelvin. Hey, wait a minute. Kilojoules per mole, we can't subtract joules per mole. That doesn't work. So we're going to have to change the unit on delta S naught from joules per mole Kelvin to kilojoules per mole Kelvin by multiplying by 1,000 kilojoules per joule. That gives us negative 2,073 kilojoules per mole minus 273 kilojoules per mole, or a standard free energy change of negative 2,346 kilojoules per mole. So we can see that because we have a large negative value of delta G naught, the decomposition of ammonium dichromate is extremely spontaneous. Finally, we're going to use that value to calculate in the second part, the standard free energy information of ammonium dichromate, because that was what we asked for in the second part. Well, for that, we're going to use the fact that the standard free energy change for the decomposition reaction equals the sum of the standard free energies information of the products multiplied by their stoichiometric coefficients minus the sum of the standard free energies information of the reactants multiplied by their stoichiometric coefficients. So this will be the standard free energy information of nitrogen gas plus 4 times the standard free energy information of water plus the standard free energy information of chromium-3 oxide minus delta G naught for the reaction we just calculated. So to calculate, oh wait a minute, I left something out. Nope, sorry, I apologize. Minus the standard free energy information of ammonium dichromate, which is what we're trying to find. So to solve for the standard free energy information of ammonium dichromate, we will rearrange the equation, and we get that that's equal to, by the way, remember that this is 0 because the formation of 1 mole of nitrogen from its elements in their standard states is 0. 4 times the standard free energy information of water vapor plus the standard free energy information of chromium-3 oxide minus delta G naught for the reaction. I'll plug in the values I have. 4 times negative 229 kilojoules per mole from the thermodynamic tables plus negative 1,047 kilojoules per mole minus delta G naught for the reaction we just calculated, negative 2,346 kilojoules per mole. And that gives me, for my final result, the standard free energy information of ammonium dichromate as positive 383 kilojoules per mole. And the fact that the standard free energy information of this compound is positive means that the formation of 1 mole of this compound from its elements in their standard states is not spontaneous. It's an unstable compound. In our next problem, we're going to use Gibbs' law, Hess's law, to calculate the standard free energy change for the reaction. 6 moles of carbon plus 3 moles of hydrogen react to form 1 mole of liquid benzene. If you'll notice, the 3 equations above it are all the combustion of the components of this reaction for which this standard free energy changes are known and tabulated. You can see that for each of these, the combustion is spontaneous because it has a negative value of delta G naught. So the question is, how do I take these equations, 1, 2, and 3, and manipulate them in such a way to see them add up to our goal equation in the yellow box? If I can do that, then I can use the corresponding free energy changes to calculate delta G naught for our goal reaction. So how do we get 6 moles of carbon, 3 moles of hydrogen, and 1 mole of benzene in their proper places? Well, to get 1 mole of benzene on the product side, I will take equation number 1, reverse it, and divide by 2. That gives me 6 moles of carbon dioxide plus 3 moles of water react to form 1 mole of benzene plus 7.5 moles of oxygen, for which delta G naught is equal to negative 1/2 times negative 6,399 kilojoules per mole. To get 6 moles of carbon on the reactant side, I'll take equation number 2, multiply it by 6. 6 carbon plus 6 oxygen forms 6 carbon dioxide. Delta G for that will be 6 times the standard free energy information of carbon dioxide, negative 394 kilojoules per mole. And then finally, to get 3 moles of hydrogen on the reactant side, I will take equation number 3 and multiply it by 3. 3H2 plus 3 halves O2 reacts to form 3H2O, and delta G for that will be 3 times the standard free energy change of equation number 3, or 3 times negative 237 kilojoules per mole. Now, let's see if we did this correctly. If I add these 3 equations together to see what cancels, I see that, get my canceling pen, 6 moles of carbon dioxide cancel 6 moles of carbon dioxide. Oh, let's see, 3 moles of water cancel 3 moles of water. I've got 6 plus 1.5, which is 15 halves moles of O2 on the reactant side, and that cancels 15 halves moles of O2 on the product side, and that gives me as my overall equation 6 carbon plus 3 hydrogen react to form C6H6, my goal equation, for which delta G naught is equal to plus 125 kilojoules per mole. So because free energy is a state function, we can use Hess's law to calculate the standard free energy change for this process. Once again, this is equal to the standard free energy information of the product liquid benzene, C6H6, because it's being formed from its elements. And again, because it is positive, that means the formation of this compound from its elements is non-spontaneous. It's an unstable compound. Finally, let's consider the third method. We've got 2 moles of phosphorus oxychloride POCl3 reacting to form 2 moles of phosphorus trichloride PCl3 plus O2, all in the gas phase. Calculate delta G for the reaction given the standard free energies information of phosphorus oxychloride and phosphorus trichloride. Well, we will use our equation delta G naught equals the sum of the standard free energies information of the products minus the sum of the standard free energies information of the reactants, each multiplied by their stoichiometric coefficients. That will be equal to 2 times the standard free energy information of phosphorus trichloride plus...
Middle school, you are dismissed. High school, you are dismissed.
Thank you, April. April just dismissed the middle school and the high school. Where were we? Plus the standard free energy information of O2 minus the standard free energy information, 2 times the standard free energy information of phosphorus oxychloride. Let me make that a little bit neater, minus 2 times the standard free energy information of phosphorus oxychloride. Once again, the standard free energies information of the pure elements are 0, so I can simply plug in, and this gives me 2 times negative 270 kilojoules per mole minus 2 times negative 502 kilojoules per mole, or delta G naught equals plus 464 kilojoules per mole. This is the standard free energy change for this process. So the question is this process spontaneous at 298 Kelvin? Let me back up for a minute and say that the only reason we could use the standard free energies information is because the problem said we were at 298 Kelvin. Well, I have a positive value of delta G naught, so I would answer the question by saying no, because the standard free energy change for this reaction is positive, and that's associated with a non-spontaneous process. Now, the value of delta S naught for this reaction is 179 joules per mole per Kelvin. At what temperature is delta G equal to 0? Does this reaction become spontaneous above or below that temperature? Explain. Let's think about this. begin by writing out the most important equation here. Delta G naught equals delta H naught minus T delta S naught. Oops, sorry. If delta G naught is equal to 0, then that means delta H naught equals T delta S naught. And we need to find what temperature that is. That temperature will be delta H naught over delta S naught. Okay? Well, we're given the standard entropy change. We need to calculate the standard enthalpy change. So to do that, let's go back to our equation. Delta G naught equals delta H naught minus T delta S naught. We know delta G naught at 298 Kelvin. We just calculated that from the previous problem. Okay, so let's solve for delta H naught. Delta H naught is equal to delta G naught plus T delta S naught. That's the positive 464 kilojoules per mole we just calculated, plus, that was at 298 Kelvin. We'll multiply that by the delta S naught that was given, 0.179 kilojoules per mole Kelvin. Notice I just converted from joules per mole Kelvin to kilojoules per mole Kelvin. And that gives me a value of delta H naught is equal to plus 517 kilojoules per mole in an endothermic process. Okay? So now that we have delta H naught for this process, we can come back up and we can plug in the temperature at which delta G naught is equal to 0 will be equal to delta H naught over delta S naught, both of which are temperature independent, remember, which is plus 517 kilojoules per mole over 0.179, sorry, kilojoules per mole Kelvin. Note, kilojoules per mole over kilojoules per mole Kelvin gives me Kelvin. My temperature is 2,890 Kelvin, and that is the temperature at which delta G naught is equal to 0, which implies the temperature at which the reaction is neither spontaneous nor non-spontaneous. It goes in neither the forward or reverse direction. So now let's go back to the question above. Does the reaction become spontaneous above or below that temperature? Well, let's look at our signs. Okay? Delta H naught is positive, delta S naught is positive. The positive value of delta H naught, that is the endothermicity of the reaction, disfavors spontaneity. But the positive value of delta S naught favors spontaneity. And we said before that such reactions are favored at higher temperature. So that temperature of 2,890 Kelvin can be thought of as the tipping point at which the reaction goes from being non-spontaneous to spontaneous. So we can conclude that the reaction is spontaneous at a temperature greater than 2,890 Kelvin, because above that temperature, the magnitude of T delta S naught is greater than the magnitude of delta H naught, and therefore delta G naught becomes negative, and the reaction becomes spontaneous. So one of the problems you can answer, knowing the values of delta H naught and delta S naught, are these, essentially. At what temperature does the reaction go from being spontaneous to non-spontaneous, and is it above or below that temperature? Okay, in the next video we will talk about non-standard